Yeah, in today's session, we'll take the fundamental theorem of arithmetic. The statement of the fundamental theorem of arithmetic, it states that every composite number can be decomposed as a product of prime numbers in a unique way except for the order in which the prime numbers occur. Now before going further, let's take what are prime numbers and composite numbers. The prime numbers are the numbers that are divisible by 1 and the number itself and are not divisible by any other number. For example, if I take a number, say 5, the number 5 is divisible by 1 and is divisible by 5 only. That is, the number 5 has only two factors, namely 1 and 5. Now say if I take another example, say the number 13. This number 13 is also divisible by the number 1 and the number itself, that is the number 13. So therefore, all such numbers which are divisible by only the number 1 and the number itself, or the numbers which have only two factors, are known as prime numbers. Now the next is the composite numbers. All other numbers which are not prime numbers are known as composite numbers. For example, if I take a number, say 8, the number 8 is a composite number because the factors of 8 are 1, 2, 4 and 8. Now in this number we see that apart from the factor 1 and the number itself, it has got two more factors, namely 2 and 4. So all those numbers which has factors 1 and the number itself and also some other numbers as their factors are called the composite numbers. Now coming back to the theorem or this fundamental theorem of arithmetic, it states that every composite number can be decomposed into a product of the prime numbers. And let's take an example, say 1260. Now whenever we want to find the factors or the prime numbers for which the 1260 is a product, we start with the lowest number or the lowest prime number 2. Now 1260 is divisible by 2, so it's 2, 6 times 12, 2, 3 times 6 and 0. So we get 2 and 630. Now again 630 is an even number, so it's divisible by 2. So we get 2 times 315 is 630. Similarly, now the number 315. Now this 315, it's not an even number, so this number is not divisible by 2. So we'll move on to the next prime number, namely 3. Now if we divide 315 by 3, we get 1 times 3 and 3 0 because 1 is less than 3 and then it becomes 15, so 5 times, so 305 times 315. Next number 105 is 335 times. Next number for 35 are 5 and 7 because 5 times 7 is 35. So we have decomposed the number 1260, which is a composite number, into a number of prime numbers as 1260 is equals to 2 times 2 times 3 times 3 times 5 times 7. It can also be written as 2 raised to the power 2 because we have got 2 2's. Similarly, there are 2 3's, so 3 raised to power 2 multiplied by 5 multiplied by 7. Now this way of representing the composite numbers in terms of prime numbers like 2, 2, 3, 3, 5, 7 is called a factor tree. Now we'll take that how to use the fundamental theorem of arithmetic to find HCF and LCM. Now HCF means highest common factor and LCM means lowest common multiple. Highest common factor of 2 or more numbers is a number which is a factor of all the numbers but is the highest among the factors. For example, if I take say 2 numbers, say 12 and say 8. Factors of 12 are 1, 2, 3, 4, 6 and 12. Similarly, the factors of 8 are 1, 2, 4 and 8. Now the common factors of 12 and 8 are 1, 2 and 4. So obviously 4 is the highest number which is common to both as a factors of 12 and 8. So therefore 4 is called the highest common factor or HCF of 2 numbers. Second term is the LCM. The LCM means the lowest common multiple. It is a number which is a multiple of all the given numbers and is the least or the lowest or the smallest number. Now suppose again if I take the 2 numbers, say 12 and 8. The multiples of 12, if I write, are 12, 24, 36, 48, 60 and so on. Now if I write down the multiples of 8, 16, 24, 32, 40 and so on. Now I see that the number 24 is a multiple of 12 as well as it is a multiple of 24 and is the least or the lowest. So therefore the LCM of 12 and 8 is 24. Now we can use the fundamental theorem of arithmetic, that is decomposing any composite number into prime numbers to find the HCF and LCM. Now suppose I want to find the HCF of 2 numbers, say 150 and 100. Now I'll write down the numbers 150 and 100 together. Now I'll start from the number 2 because the number 2 is the smallest prime number. Now since the number 2 divides both 150 and 100, it is 275 times 150 and 250 times 100. Now I get the numbers 75 and 50. Now here 75 is not divisible by 2, whereas 50 is divisible by 2. So we have to remember whenever we find the HCF to divide using only those prime numbers which divides both the numbers. Now since here 75 is not divisible by 2 and 50 is divisible by 2, so we can't take the number 2. Now we'll move on to the next number. The next prime number is 3. Here 75 is divisible by 3, but 50 is not divisible by 3, so therefore we'll not consider 3 also. Then we'll move on to the next number. The next prime number is 5. 5 divides 75 and 5 divides 50 also. So therefore we'll take the number 5. Now 5 15 times is 75, 5 10 times is 50. So we get 5, 15 and 10. Now the number 15 is divisible by 3, but the number 10 is not divisible by 3, so we'll not go for the number 3. So we'll move on to the next number. The next number after 3, that is the prime number. Next prime number after 3 is 5. So therefore we'll take 5. 5 3 times 15, 5 2 times 10. Now 3 and 2 are prime numbers, so obviously these two numbers are not divisible by any number. So therefore the highest common factor or the HCF of the numbers 150 and 100 is 2 times 5 times 5, that is 50. Will not take the numbers 3 and 2 because these are the numbers which divides one particular number and not the other numbers, because 3 divides 15 and is not dividing 10, and 2 divides 10 and is not dividing 15. So we will not consider 3 and 2, will consider only 2, 5 and 15, 2, 5 and 5, because only these numbers divides 150 and 100 completely. So therefore the HCF is 50. So one thing one should always remember while finding the HCF, will divide the numbers by only those prime numbers which divides both or all the given numbers, and will go on dividing till we reach the numbers which are the prime numbers. Now the same fundamental theorem of arithmetic can also be used to find the LCM of two numbers. LCM means the lowest common multiple. Now suppose again we take the two numbers 150 and 100 and want to find the LCM of two numbers. Here also we'll start from the smallest prime number, that is 2. 75 times 150, 50 times 100. Now here 75 is not divisible by 2, whereas 50 is divisible by 2. So we take 2 because in case of LCM, even if one of the numbers is divisible by any prime number, we divide that number by that prime number and leave the other number as it is. For example, in this case, 75 is not divisible by 2, but 50 is divisible by 2. So we'll continue dividing it by 2. So 75 as it is, because it's not divisible by 2, 25 times 50. Now the next is 75 and 25. None of the numbers is divisible by 2. So we'll move on to the next number 3. 25 times 75. 25, because 25 is not divisible by 3. So we have moved 25 as it is down. Now we get 25 and 25. Both the numbers are divisible by 5. So 5 times 5, 25, and again 5, 25. Now here also both the numbers are divisible by 5. So 5, 1 and 1. 1 and 1 still are not composite numbers, so we'll stop the process here. So we get the LCM as 2 times 2 times 3 times 5 is equals to 300. So the HCF, or the highest common factors of the two numbers 150 and 100, is 50, and the LCM, or the lowest common multiple of the two numbers 150 and 100, is 300. Now, one of the most important properties of HCF and LCM is the product of HCF and LCM is always equals to the product of numbers. Now we can check this fact. Now here HCF is 50 times LCM is 300 is equals to 5, 3, 15, it's 15,000. Now if we take the numbers are 150 times 100, it's also equal to 15,000. So therefore one should always remember, if we have two numbers and if we take the product of those two numbers, it's always equal to the product of HCF and LCM of those two numbers. Now we'll take a few problems related with the fundamental theorem of arithmetic. Now suppose the question is, it's given that for the two numbers 306 and 657, the HCF is 9. HCF of 306 and 657 is 9, and the LCM of those two numbers 306 and 657 we need to find. Now, just now we did that if we have the HCF and LCM of two numbers and take the product of those two numbers, that is HCF and LCM, the product of HCF and LCM will always be equal to the product of the two given numbers. Now, so therefore we can write as HCF times LCM is equals to the product of numbers. Now HCF is 9, so 9 times LCM we don't know is equals to the product of the numbers. The numbers are 306 and 657. So therefore we can write 9 times LCM is equals to 306 times 657. Now bringing this 9 down over here, we get LCM is equals to 306 times 657 divided by 9. Now 34 times is 306. So we get LCM is equals to 34 times 657, which is equals to 22,338. So therefore, if we have two numbers 306 and 657, then the HCF will be 9 and the HCF will be 9 and LCM will be 22,338, and if we multiply the HCF, that is 9, with the LCM, that is 22,338, it will be equal to the product of 306 and 657. Similarly, we can find the HCF if LCM is given by using the same method. Now, one more type of problem that we can solve using this theorem, the fundamental theorem of arithmetic. Now, suppose we want to check whether a given number is a composite number or not. Suppose the question is, explain why the number 7 times 11 times 13 plus 13 is a composite number. Or suppose we want to check whether this number is a composite number or a prime number. Now the number 7 times 13 times 7 times 11 times 13 plus 13 can be written as 7 times 11 plus 1 times 13, because here 13 and here also 13 is common, so we have taken it outside. So if we take 13 out from here, we get 7 times 11, and from here if we take 13 out, we get 1. So we get 7 times 11 plus 1 times 13, which means that this given number is a multiple of 13, or the number is divisible by 13, or we can say that this particular number has a factor 13. Now, if we look at the definition of prime number, the definition of prime number says that for any given number, its factors are only 1 and the number itself. And if for any number, if it has a factor which is other than 1 and the number itself, the number is a composite number. So in this problem, this particular number has a factor 13 which is other than the number itself and the 1. So therefore the number is a composite number. Now suppose, let's take one more example. Suppose we want to check whether a number of the form 6 raised to the power n can end with a digit 0 for any small n belonging to capital N. It means we have a number 6 raised to the power n. If we take, say, n is equals to 1, it is 6. If we take n is equals to 2, we get 6 raised power 2, that is 36. If we take n is equals to 3, we get 6 raised power 3, that is 216, and so on. Now we want to check whether for any value of n will get some number where it will end with 0 or not. Now the number 6 raised power n can be written as 2 times 3 raised to the power n. This can be written as 2 raised power n times 3 raised power n. Now we know that if we have a number 2 raised power n, this number will never end with 0. The reason is, for any number which is a multiple of 2 and it should end with 0, it has to be a multiple of 5, because 2 times 5 is equals to 10, that is a number ending with 0. I'll repeat once more. If there is any number 2, if any number is in the powers of 2, then it will end with 0 only if it can be expressed in the powers of 5, because 2 into 5 is equals to 10. So since here we don't have any term of the form 5 raised to the power n, so therefore we conclude that this number will never end with 0. Therefore we can say that the number 6 raised to the power n will never end with a digit 0, whatever value for n we take from the set of natural numbers.